In this video, we are going to calculate the moment of inertia, this time of a spherical shell. So imagine you're having something like a ball. A ball is a good example of a spherical shell or a hollow sphere, which means it's a sphere and there's no material inside, it's just a shell. So the idea, just as we did for a solid sphere, is to slice, a very thin element of the sphere that reflects the symmetry of the sphere. So here, if we just take a thin slice of the ball, for example, you see that we're going to have this tiny ring, okay? So it's like a disc with a tiny, with a small thickness, so that actually it approximates to a ring. So what we can do is we can calculate the moment of inertia of this ring about this axis, and then just sweep by integrating all through the surface of the shell. So due to symmetry, again, the moment of inertia of the shell about any axis that passes through the center is going to be the same. So whatever the axis that you decide to choose, the moment of inertia is going to be the same. So we can start by writing, we can denote sigma, okay, the mass, the uniform mass distribution. So sigma is going to be the mass of the shell. So let's say the shell is of mass capital M and radius capital R, and that our element has a mass of dm, okay, and a radius of small r. Hope you can see that. Okay, so yeah, we can write that sigma is the mass of the shell all over its area. The area of a shell is just the area of a sphere, which is 4 pi radius squared. Okay, and then this should also be equal to the mass of the element, which is Zm, all over the area of the element. But then here we need to be careful, okay, because this element is actually a ring. So what we need to do if we want to calculate the surface of that ring, we first need to calculate the circumference. The circumference is just 2 pi radius, okay? So this circle, and then we'll multiply that by this thickness. And that thickness is just this length of arc, this tiny arc length that you can see here. So if we denote theta, okay? So if we denote theta, I don't know, this angle, I ought to have illustrated it here. So maybe let me just represent it so that it should be clear. So if we denote this angle theta, okay, then you can see that this tiny, the tiny angle that will be formed here is going to be d theta. So this arc length is going to be r times d theta. Hope you can see that. So it's just the length of arc. You take the arc length and then you sweep it through a tiny angle d theta. So that makes r d theta is this arc length. So here we have the circumference times r d theta. Okay? Which means that dm can be written as m on 4 pi r squared, okay, times 2 pi little r, then capital R d theta. And if we simplify this further, we are going to have 2 pi that cancels 2 here. R cancels 1 r, so we get m on 2r times little r d theta. Okay, so that's the mass of the element. Then if you want to calculate the moment of inertia of the shell, that's just going to be the integral of the moment of inertia of the ring. Okay, so let me say I of ring. Then you remembered that the moment of inertia of a ring, we calculated that in a previous video. If you haven't watched it, I will leave the link somewhere up here so you can go and watch it. So the moment of inertia of a ring is just, I can recall that. So I of a ring is just the mass times the radius squared. So we can just apply that formula here. Our mass is dm and the radius is just little r squared. So we need to integrate that over all the mass. Okay, so that gives us the integral of r squared times capital M over 2r times little r d theta. And we need to integrate over values of theta. Okay, so if we simplify this further, we are going to have an integral. Okay, we can keep this constant out of the integral because it's a constant. So we have m over 2r times the integral of r cubed d theta. Okay, so you see that we have an integral, we have two variables, r and theta. We need to establish a relationship between little r and d theta before we can integrate over all the values of theta. Okay, so to do that, if you look into this triangle, let me zoom in a little, you'd see that we have something like this. Okay, we have that, so we have a right angle triangle. So if I zoom into this tiny portion, here we have theta, here we have r, here we have capital R. Okay, so we can see that what relates little r and capital R is the sine, so sine of theta is little r on capital R. So we can make use of this to further simplify this expression. So that's just going to give us I of the share as m over 2r, okay, times the integral of little r cubed, so that's going to be capital R sine theta cubed times d theta. And then can you guess what should be the boundaries of theta if you want to generate the whole share? Yeah, you see that we need to take, theta has to go from 0, okay, like that, and then all the way around to pi. If we move theta from 0 to pi, which means from here, so if theta goes from here to here, so like, how can I do that? So like this, so from here and then right all the way to the other point like that, you see that this ring is going to move from this point to this point, and that generates the whole surface of the shell. So indeed we need to go from 0 to pi. So we can simplify that. We're going to have m, then we have an r cube here that simplifies that. So we're going to have m over 2 times r squared integral from 0 to pi of sine cubed theta d theta. Okay, so from this point you can decide to perform this integral yourself, or you can just look for the value of this integral in a table. Okay, so I'll just give you the result of this integral, which you can, if you want to integrate it yourself, then that's a nice exercise of integration. You need to use a substitution. Okay, but then this is not like what interests us here, so you can just look for the value of this integral in a table. And that's just 4 over 3. Okay, it's the value of this integral. So this integral is 4 over 3. So if we simplify that, we are going to have 2 over 3 mr squared. So I share is 2/3 mr squared. And this is the moment of inertia of a shell about an axis passing through its center. Okay, hope that's clear. The derivation is really not difficult. You just need to understand how to properly select your element and then integrate with the appropriate, by choosing the appropriate variable and the appropriate bounds to generate the whole structure, in this case of the shell. Okay, hope that's clear. If you have any questions, feel free to ask in the comments and I'm going to reply you as soon as possible. All right.